All right, so we continue our network security course with application layer. In order to talk about security, first we have to cover all of these layers. Then we will talk about the security. So we are still using the lecture slides from the book Computer Networking, a Top-Down Approach by Jim Kurose and Keith Ross. Of course, I just modified some stuff, added a few things and removed some of the stuff that are not going to be related to us. So I will not be talking about peer-to-peer applications or video streaming, but we will try to cover all of these topics, all of the remaining ones. So we start with principles of network applications. So recall that the book starts with a top-down approach. So we divided the internet into layers. So we are at the top layer now, application layer. And this is the, the one we are more familiar with because we are using all of these applications. But this also means that when you want to write an application for the internet, you should know how it works, right? You should be familiar with the application layer. So our goals are conceptual and implementation aspects of application layer protocols, transport layer service models, client-server paradigm, peer-to-peer paradigm. And our goals are to learn about protocols by examining popular application layer protocols and infrastructure like HTTP, SMTP, IMAP, DNS. And then again, I'm not going to cover video streaming systems, but if you're interested, the book has nice content with the slides also about Netflix and how it works and so on. Yes, and finally, there will be a simple example, a Python example to show you how you can do programming by using Socket API and so on. Yes, let's start with some network apps. So there are many stuff we are using right now, like social networking, most probably the dominant part of the internet right now. Web, text messaging, email, multi-user network games, streaming, stored video like YouTube, Hulu, Netflix, and peer-to-peer file sharing. Of course, due to pandemic, we use more voice over IP than before. Also real-time video conferencing, which is we are just doing right now. We are teaching physically and at the same time over the net. So this is again a Zoom session. Internet search, remote login, and so on. So actually, initially, so this wasn't the case. Initially, people were trying to use, remote login to other computers. I'm talking about, 1970s and 80s, or send emails, because these were the things that needed, like for universities wanted to communicate with each other and so on. So aim was to, file sending and receiving and so on. But of course, web broke the system. So this is why HTTP is important. So initially, when there was the internet, there weren't actually web. No, it was just somebody's idea. You can read the paper if you want. But with RFCs, we define all of these protocols. So this is why you have these systems. So in order to understand HTTP, you have to look at the related RFC to see how it works. And actually, web browsers also employ that RFC. This is why every web browser shows you almost the same web page when you visit them. In the past, there were some problems because, Netscape and Internet Explorer actually showed you somewhat different web page due to some different implementations, let's say. Okay, so let's talk about creating a network app. So we write programs that run on different systems, right? So we looked at this picture before, right? So we have end systems, GSM antennas, routers, and so on. So we are now looking at the end systems. And we have at the end systems like our laptops, mobile phones, and so on. We divided the internet into 5 layers. So actually, these devices start with the application layer, and this is the part we want to write the application, right? Good thing is that we don't need to think about the rest of the layers when you are actually implementing. Right? So, but another important thing is that the application you write will run on different end systems. Because, if you're visiting a web page, you can do it with your mobile phone. You will be using a different browser there. In your laptop, you will have something else and so on. So, but different hardware, different software, different operating systems, but they should, still could communicate in a proper way. For example, web server software communicates with browser software. No need to write software for network core devices. Network core devices do not run user applications. Application on end systems allows for rapid app development propagation. So this is important. Here what we are trying to say that when you write an application, actually you don't write the code for the network layer or data link layer. Actually, if you wanted, you couldn't do anyway because routers would not listen to you, right? So this is the good thing. So you only focus on the application layer, you write your system, write your program, and this actually speeds up the things. If you were to, consider the other layers, it would take a lot of time to, create a multiplayer video game and so on. So we divide the system into server and clients. Actually, servers and clients can be also both server and client at the same time. But one side is requesting something, and the other side is, giving the stuff they want. So this is why we call them client and server. So server always on host, permanent IP address, often in data centers for scaling. So at the beginning of the internet, actually, we didn't have that many servers. So actually, you use your computer at home, your personal computer, as a web page, for instance. When you turned off your computer, then people would not be able to visit your web page. So that was the idea. But we moved on to hosting systems and so on. So we're now keeping them at a server. But with Web 2.0, instead of creating our own servers, we said that, okay, this is too much stuff. Let's give all of our data to service providers like, YouTube, Facebook, Instagram. So instead of creating your own web page, you simply, put your content on these social media web pages, and they are always on. So this is why most of the time they are in data centers, because otherwise they couldn't, keep up with the load. To avoid, denial of service attacks, you have to have a huge data center. And so in data centers, actually, there won't be a simple desktop PC like this, but thousands of servers. This is why, Facebook and, Instagram can serve you with that speed. Client-side contact, communicate with server, may be intermittently connected because you can turn off your computer anytime you want. You can turn off your Wi-Fi and your mobile phone and so on, so you don't have to be connected all the time. May have dynamic IP addresses. This is actually the default for users. If you want a static IP address, for instance, for the internet service provider, you have to pay monthly a more fee so that they can assign you a static IP. Okay? So if you, in the past, we did that. We paid more and created our web pages. But then we said that keeping up your own server is, maintaining it takes a lot of time. This is why we moved on to hosting services and social media web pages and so on. Do not communicate directly with each other. This is actually a simple statement, but for me this is very important because everybody is using the internet and they don't know this. For instance, assume that here somebody has a mobile phone, and let's say that you have WhatsApp app in your desktop or laptop. So when somebody sends you a WhatsApp message, they think that since all of these devices are connected to internet, they think that this message somehow, follows some path and reaches to you. So they think that there is nobody in the middle. But actually what you do is you send your WhatsApp message to WhatsApp server, and the server sends it to you. But this is very important because this makes it centralized. Okay, this is the main difference between centralized and decentralized. This is important because when we try to explain how Bitcoin works and we say it is decentralized, people don't understand it because people think that everything is decentralized on the internet. But on the contrary, almost is centralized. Almost everything is centralized in Web 2. Okay. So here examples are HTTP, IMAP, FTP. By HTTP, you can think that this is a server hosting a web page. So probably they have an Apache server installed. So you request the web page and they give it to you. Or maybe you want to download the file. You can create an FTP connection. So these are all of them are protocols. So there are RFCs for all of them. You have to look and check. So for the emails, we will see IMAP and so on. Okay, so peer-to-peer architecture is somewhat different. In this case, since all of the devices are connected to internet, we don't require a central authority to transfer the data. We can directly communicate with each other, since everybody has an IP, which we will be talking about next time when we talk about transport layer. But we know that the address, IP is the address of the device, so you can directly send data to them and receive them. So you don't need a central authority to do that for you. This is the good thing of the peer-to-peer architecture. No always on server. Somebody can turn off their device and get disconnected. Arbitrary end systems directly communicate. Peer request service from other peers. Provide service in return to other peers. So for instance, in BitTorrent, you share files, but you also download files. So you provide the service to both of them. But also in vehicular ad hoc networks here, a car actually sending data to other cars saying that this road is has no traffic. But others also say that I'm on this lane and it has traffic, so you just change your course and so on. So people provide service and receive service this way. Self-scalability, new peers bring new service capacity as well as new service demands. Because think about BitTorrent, new users, new peers will request to download more files, but maybe they will put files that weren't hosted before. And of course, this was important like 5 or 10 years ago because people were downloading a lot of music and movies, which were illegal most of the time. But nowadays, people, just it takes too much time for people. They just want to visit a web page and watch the movie. This is why they prefer more streaming services. Peers are intermittently connected and change IP addresses. Complex management, because each device changes their IP addresses, because I told you that end systems are generally have dynamic IP addresses. Turning off your computer or your, actually not your computer, but turning off your modem router at your home and turning it on actually changes its IP address. So this is why you have to manage it all the time and so this is why you have to keep trackers and so on and so forth. Example is peer-to-peer file sharing, and I already explained almost everything, so I will not go much more detail into peer-to-peer architecture, but you have to, at this part you have to think, if I'm going to create an application for the internet, will I be using client service paradigm or peer-to-peer architecture? So this is the first thing you have to decide first. Okay, this is why I'm showing to you, and this is why you can create an application that nobody designed before. You can change the system, how it works. Think about WhatsApp. Actually, when you think about it, you are simply sending messages over the internet. But until that part, nobody did it in a good way. So this is why we didn't have such a service. Actually, you could have it like in 1990s, right? The internet is the same, but somebody should come up with a clever idea, but also implement it in a secure way. So you can do the same. You can come up with a good peer-to-peer architecture system. Bitcoin is a very good example. Somebody said that why not keep digital financial data distributed with the peers. So this was a very good idea and change the system. So you can come up with many different ideas. If you're interested, you have to first decide how it will work. You can do server client paradigm or peer-to-peer architecture and so on. So we say that process is communicating because if you go back, you're running a program application here and the server or the client peers, whatever, they are running applications. So actually in the operating system, we have processes and those processes are communicating. So a process is program running within a host. Within the same host, two processes communicate using inter-process communication defined by the operating system. Processes in different hosts communicate by exchanging messages. So this is where the internet comes into play. So, we say client and server, but of course, both of them are, end devices. We say it client because it is the process that initiates communication. So if you want to visit a web page, you are the client and the host that gives you the web page data is the server. So this is how we define them. But a server can also be a client. A client can also be a server. Note that applications with peer-to-peer architectures have client processes and server processes, because for instance in BitTorrent you are downloading a file but also sharing it, so you're both the client and the server. For this reason we call them peers. So sockets are important. Process sends, receives messages to and from its socket. So at the application layer you have a process and it wants to communicate with the process on another device application layer. So you want to transmit data over the internet and they will understand it. And for this reason, we are going to use sockets. So you can think about it as a door. So from your application, you give it to the transport layer, and this way, it goes the whole way. So yeah, socket analogous to door. Sending process shows messages out the door. Sending process relies on transport infrastructure on the other side of door to deliver message to a socket at receiving process. Two sockets involved, one on each side. So here you're sending it, and this one is also receiving from this door, but also send their data, they reply from here too. Okay. So let's look at addressing processes. To receive messages, process must have identifier, right? Host device has unique 32-bit IP address. So we will talk about it at the transport layer. Just know that at this point you have 32-bit. Of course, here we are referring to IP version 4. With IP version 6, things will be somewhat different. But just saying that we can, uniquely identify every host with 32-bit IP address. But if you go back now, that 32-bit IP address actually represents this device. But you want to communicate with a specific application process. So sending it to the IP address will not be enough. That's operating system should know which process it should communicate to. So for this reason, we have sockets and so on. So question is, does IP address of host on which process runs suffice for identifying the process? Of course not. This is what I was trying to say. Answer is no. Many processes can be running on same host. Actually, thousands of processes are running on your operating system. You can just, if you're using Windows, just open the task manager and you will see that many processes are running on the background. Identifiers include both IP address and port numbers associated with process on host. So we define port numbers at the network layer, so that this is how we transport them. And a socket actually can be thinking about the combination of IP address and the port number. Okay, so we have some default port numbers, like for HTTP server, it is 80. So when you want to visit a web page, probably the server is running an Apache server and listening at the port 80 to all of these communications. Mail server is 25, but of course this is unencrypted port. If you are using secure email, then probably it will be like 925 or something. So you can easily understand if it is encrypted or not by looking at this number. If it's 900, most probably it is encrypted. To send HTTP message to, for instance, this university's web server, the IP address will be this and port number will be this. Okay, so your process actually creates a socket to this, and so this way you have the destination and the source and so on. So an application layer protocol defines type of messages exchange, for example, request, response. So we have a infrastructure to communicate, but now you have to design protocols so that they will determine what kind of messages you will exchange. So this is why the protocols are important. Message syntax, what fields in messages and how fields are delineated. This is also important, depends on the application. Message semantics, meaning of information in fields. Rules for when and how processes send and respond to messages. Open protocols, defined in RFCs, everyone has access to protocol definition, allows for interoperability, for example, HTTP, SMTP. So this is important. For instance, for the HTTP, you have RFCs. So this is why browsers can, implement every stuff that is defined in the RFC, so we can visit every web page. So this creates interoperability. So if some country uses a different protocol, then you wouldn't be able to visit those web pages and understand what it is, right? Because here you are defining how it works. But if you're a company, you don't have to rely on the open protocols. You can create your own protocol, like Skype and Zoom. So you cannot go and download the protocol that the Zoom is using. Okay, as long as they don't open publish a white paper or something. So in your application, you have to also think about it. Will you going to use an open protocol or will you define your own? Okay. So what transport service does an app need? Data integrity, because at the application layer, you are creating your application, but you then send it to transport layer, right? So you want some properties from the transport service. So one thing you might require is data integrity. And this is, of course, important because in some applications, actually in most applications, for example, file transfer, web transactions, require 100% reliable data transfer. Because if you download a file, for instance, 2 gigabytes of file, but think that 5 bytes of it are corrupt. So you don't have any integrity. So you wouldn't be able to, use that file most probably, right? You want an integrity. But in some cases, like other applications, for example, audio can tolerate some loss. Think about, a phone conversation or like a Zoom conversation we are having here. So at some point, if you hear a glitch or saw a glitch in the video, you wouldn't mind, it wouldn't, change the whole process. So you can, tolerate some loss, but of course not much. So data integrity might be suitable for some applications and not that important for some other applications. Another thing we might need is timing. Some applications, for example, internet, telephony, interactive games, require low delay to be effective, right? Because if you have high latency, if you are playing a video game, you wouldn't have the proper interaction, so you wouldn't like it. Also for the telephony, for instance, if your interconnection is bad, think about, nowadays our infrastructure is a lot better than before the pandemic, but like 10 or 5 or 7 years ago, when you call somebody via WhatsApp, most of the time you will have, you have to wait a few seconds so that, because there is a latency and so on. So it is not as like GSM communications, right? Because in the GSM communications, last week I explained, we have circuit switching, but in the packet switching, you have delays. This is the main difference. So in internet, unfortunately, we cannot guarantee the timing. For instance, some people are watching this Zoom conversation, and maybe some of my video or voice will reach them a few seconds later. We cannot guarantee like 10 milliseconds, right? We cannot do that. Throughput is important. Some applications, for example, multimedia, require minimum amount of throughput to be effective. For instance, if you are watching a YouTube video that is full HD or 4K, you have to have enough throughput to do that. Otherwise, you can watch like 5 seconds, wait for the buffer to fill, then watch another 5 seconds, and wait 10 more seconds to download it, and so on. Some other applications are elastic applications, make use of whatever throughput they get. So I will show some examples, but file downloading is like this. You start downloading, maybe due to some problem, at the beginning you start downloading in a fast way, then it's slowed down. But you will wait at the end. You don't mind if you receive the file in 10 seconds or 11 seconds, right? It is not that important. So you can tolerate that kind of throughput. Security, very important. You can have encryption, data integrity, authentication, data authentication, and so on and so forth. So this is the stuff we will be covering in the following weeks. This is the important part. But the funny thing is that internet initially does not support this. So as you can see, we will see here some examples. So think about applications like file transfer, download. You cannot tolerate data loss. Throughput is elastic. Time sensitive, no, you can wait. Email is the same. Web documents is the same. If you are doing real-time audio and video, like the one we are doing right now with Zoom, you can tolerate some loss. You have to have some guaranteed throughput. If, for instance, if my throughput were less than 2 megabits per second, I wouldn't be able to, have this conversation in full HD in a proper way. Also, you should have at least some throughput for that. You might think that there's a huge gap between these parts. You might think why this is the case. This is actually about the compression. Think about DivX. What actually now happens is that you can look at the screen and see my video on the right top, right? So actually this part is changing, right? I'm talking, I have hand movements and head movements. Actually only this data is transferred right now. The remaining part, the slide, is the same. So you're not transferring any data. So think about it as a full HD screen, and I'm only sending a small part of pixels to the other parts, saying these pixels are changed. So actually this is the thing. When I end this session and record this video, it will be like 30 minutes video, but it will be like 40 megabytes on the hard drive. But if if I had my video on the whole screen, it will be maybe hundreds of megabytes. This is why currently you don't need much throughput, but you can tolerate also some delays. Time sensitive, yes. If it is more than 100 milliseconds, then it will be meaningless, right? Because currently, of course, I'm only the one talking right now, but when we will have the question answers, if I talk and if you hear it 1 second later, if you try to say something, we will talk over our voices, right? This is the thing. So you should have some guarantee. But again, nobody can guarantee this. This is why in multiplayer video games, here interactive games, you prefer to have around 10 milliseconds. So this is why if you're in Europe, you connect to the server in Europe. You don't connect to a USA server because now you have to pass the ocean, which directly gives you like 100 milliseconds latency. So this is the thing, okay? And there are some other examples, as you can guess, right? So Internet Transport Protocol services, there are two famous ones, TCP service. So we said, so far I told you what we wanted, so let me go back. So we would, prefer data integrity, timing, throughput, and security. So let's look at if the transport protocol services provide that. So let's look at TCP service. Reliable transport between sending and receiving processes. So here we have reliability. Flow control, sender won't overwhelm receiver. This is the good thing with this protocol. If you send data, if your connection is good and sending too much data, but the person who's downloading may be having a problem with their throughput, so you don't have to overwhelm them. So this way you actually have a flow control and send data in a slower way. You can see this actually in YouTube. You can watch a YouTube video and choose the video resolution as auto, and if your connection is good, you will see it like the top version. For instance, maybe it is 1080p, full HD. But if if you have some connection problems, you will see that it will automatically lowers itself to 720p or even 360p. This comes from the flow control. Also the congestion control, throttle sender when network overloaded. Connection oriented, setup required between client and server process. So if I'm using TCP as my transport protocol, I have to first create a connection. Like in the people communications, we said somebody says hello, the other one says hi. This way you create the connection, right? Here we also have to do that with the TCP, and we will see some examples in a second. So, but the problem is that it does not provide timing, minimum throughput guarantee, and security. So I already mentioned the timing and minimum throughput guarantee. I mean, throughput depends on all of the links. So we already talked about this. Maybe even if you have a good link, your internet service provider charges you money for the service, right? Maybe you pay less and you get small throughput. And again, before the pandemic, we had very bad throughput in Turkey, but nowadays it is better. When I was first teaching, I realized that my upload speed was like 2 megabits per second, but of course this is theoretical upper bound. So it was very hard to communicate, and it also depends on the country. In some countries we still have very poor connection. So we have packet switching, so we cannot guarantee timing, we cannot guarantee throughput, but we also does not provide security with TCP. This is important. This is why we will talk about TLS and so on to provide security. UDP is somewhat different because it is unreliable data transfer between sending and receiving process. So I mean, this means that you're sending the data, but it may be lost. Okay. Does not provide reliability, flow control, congestion control, timing, throughput guarantee, security, or connection setup. So at this point, you might say that then why we use it, right? Because it doesn't provide anything. Yeah, question is why bother? Why is there a UDP? Okay, so let's look at some examples again for the applications and application layer protocols and look at which transport protocol it uses. So file transfer, you can use FTP. Again, there is the RFC here. It uses TCP, as you can imagine, because we need reliability, right? Email, SMTP protocol, TCP. Web documents, HTTP. It also uses TCP. Internet telephony, again, here, if you want reliability, you can use TCP, but you can also prefer UDP. Streaming audio, video, HTTP or Dash. This is what actually most streaming services like Netflix and so are actually using. If you're interested, you can look at it. It uses TCP. But in the interactive games, here WoW means World of Warcraft, I guess, or first-person shooters, I guess. FPS is for that. But so there are proprietary, every company actually using their own applications. They can be UDP or TCP, but we will, as an example, see DNS, which is UDP. Then you might see that we are really using UDP at some point. But you can also guess that since there's no, here I said that setup required between client and server process. Here you don't need it. This is why it is actually more faster. Okay, securing TCP, this is the problem because we talk about our needs, we talk about what the transport layer provides, and we observe that both TCP and UDP does not provide security. This is important because some people think that UDP does not provide security, but in TCP we have security, we don't. Okay, vanilla TCP and UDP sockets, no encryption, clear passwords sent into socket, traverse internet and clear text. So this is what happened in the 1990s. Okay, 1990s. So you, for instance, you created an account for a web page, but you were communicating via TCP. So when each time you log in, you wrote your username and password there, and actually this data transmits from you to the web server. So anybody listening in the middle actually could capture your passwords and usernames. FTP is an example to this. You can capture a lot of FTP username and password. And the problem is that generally, if you have a web page, you create a username and password for the service, but you also use the same thing for the FTP. So whenever somebody captures your FTP password, they also, capture your web page and, write funny stuff and say that this web page is hacked by this group and so on. So this is why, FTP connection at an airport was a guaranteed attack, just, use an FTP service at an airport and it takes like a few hours to see that your web page is attacked. So this is because no encryption. Transport layer security, TLS actually solves this problem, provides encrypted TCP connections, data integrity, and endpoint authentication. So in order to talk about it, we have to talk about encryption, data integrity, algorithms like hashing, message authentication codes, or also authenticated encryption and so on. So we will cover the required cryptography, and then we will see how all of this cryptography is used on the internet. TLS implemented in application layer, but it works as if it is in the transport layer. This is the good thing. So when you create an application, you can simply say, use the, TLS libraries that use TCP in turn, and this way you have, security. So you don't have to deal with that at the end. So clear text sent into socket, traverse internet encrypted, and at the receiver side, they decrypt it back, and this way you communicate. So more after we talk about cryptography here, because I haven't teach encryption yet, so we will see it later. Okay, so this was about the principles. We will continue with web and HTTP.